Hi, good morning, everyone. This is Dr. Sharif El-Gamal again with you. And today I'm going to discuss with you how to design pad footings under axial load. Okay, please don't forget to subscribe, and share the video with others to share the knowledge. As we discussed in our previous video about footing, we have different types of shallow foundations. This include pad footings, combined footings, strip footings, mat foundations, and there are also other types of shallow foundations. In this video, I'm going to concentrate on pad footings. And as you know, pad footings, we could be a square, could be a rectangular footing. When you have a footing supporting only one column, we call this is pad footings. For pad footings, you may have two different types of loading. The footing can support only axial load. In this case, the load will be as a force in kilonewton, and the pressure under the footing will be uniform pressure. In this case, the value of this pressure equals force divided by the area of the footing, so it will be N divided by A. Or if we said the footing is B by D, so it will be N divided by B times D. The second case, when you have the footing supporting axial load and moment, or we call it eccentric loading. In this case, the distribution here will not be uniform. It will be a linear distribution. You have a higher value here and a lower value here using these two equations. In this video, I will be talking about designing of pad footing under axial load. In a coming video, I will discuss the second case when we have eccentric loading or axial load plus moment. Okay, to discuss this first case when we have an axial load only, we will take an example here and we will solve it step by step to let you understand every point here. So what do we have in this example? It is telling us that there is a footing it is required to design a footing to resist characteristic axial load of 1000 kilonewton dead load and 350 kilonewton imposed load from a 400 millimeter square column. Bearing pressure of the soil is 200 kilonewton per meter square. The FCU F35 F field is 460 megapascal. And so the idea here, we need to design this footing. The column here is 400 by 400, and the bearing pressure is given the dead load and live load. So let's start making a solution. To start any solution, you have to define the data that you have and what is exactly required from you. So the data, we have a dead load of 1000, live load of 350 kilonewton. We have a square column of 400 millimeter side. The bearing pressure is 200 kilonewton per meter square, and FCU F35 F field is 460. So what are the steps? If you want to see the steps, you can go back to the previous video. But the idea here, first of all, we need to find the edge, the height of the footing, okay, a suitable edge. Then we will get the area of the footing, B and D. Once we got all the dimensions, we can start by designing for reinforcement in both directions. Then we have to check direct shear or one-way shear, and then we have to check the punching shear. Finally, we have to draw the footing and show the reinforcement. So let's start by calculating H first. So first step, calculating the footing depth H, and from H we can get the effective depth, which is D. Calculating the H, we have to do this using ultimate limit state. So the load that we are going to use to calculate the H here, it will be the ultimate load, not the service load. So to do that, we have to get the N ultimate. According to the British standards, the N ultimate equals 1.4 dead load plus 1.6 live load. So it will be 1960 kilonewton. If you are using any other code, okay, the only factors here will be changed, but it will be the same solution, will continue the same solution. Okay, so this is the ultimate load, 1960 kilonewton. Then we have to get the ultimate shear stress or ultimate shear strength of the concrete here. So as you know, V ultimate equals the lesser of two values, 0.8 square root of FCU or 5 Newton per millimeter square. So the lesser from here, it will be 0.8 square root of 35. It will give you or give us a value of 4.7 Newton per millimeter square. Why we need this one? It will be a guide for us to get the D, and from the D we can get the H. So the idea here that I explained in the previous video, we will assume that the shear stress at the surface of the column will be half of this value. It will be V ultimate divided by 2. This is why we got V ultimate first here, and then we'll divide it by 2. Okay, to do that, we have to get the perimeter of the column. The perimeter of the column equals 4 times the side of the column, because this is a square column, so it will be 4 times 400. Here it's equal here. 4 times 400 equals 1,600 millimeters. This is the perimeter of the column. Okay, then the shear stress at the face of the column equals the force divided by the column perimeters times D. Any stress equals force divided by area. The area here, it will be the column perimeter times the depth. So in this equation, we are going to replace the stress. We assume the stress or the shear stress will be V ultimate divided by 2. So we are going to replace V by 4.7 divided by 2. N also is known. Column perimeter also is known. So the only unknown will be the value of D or the depth of the footing. So doing that, V ultimate equals 1,960. Okay, don't forget to multiply by 10 to power 3 because this is kilonewton and we need to have it as Newton, because here we are going to use this value is millimeters and the shear here is per Newton per millimeter square. So don't forget here to multiply this kilonewton by 1,000. So all of this equals the V ultimate divided by 2, 4.7 divided by 2. By solving this equation, the only unknown will be the depth of the footing. We calculate the D. In this case, the D equals 521 millimeter. Okay. Once I have the D, we can calculate the total H. So the H of the footing equals the depth plus the cover plus the diameter of the bar. So assuming that we are going to use blinding concrete layer, so the minimum cover in this case will be 50 millimeter. If you are not going to use blinding concrete, so the minimum cover will be 75. Here we assume, or we will use blinding concrete, so the cover will be 50. And assuming that the diameter of the bar, 20 millimeter bars that we are going to use in the footing. So from here we can calculate the H equals D plus cover plus the diameter of the bar. So it will be 591 millimeter. So let's round it up. So it will be 600 millimeter. Once we rounded the H here, we have to recalculate the D. So the D equals H minus cover minus the diameter of the bar. So it is 530. So this, we can call it initial proportioning step to get the H. Okay, or step number 1, we need to get the H and the D. And we got the H here equals 600 and the D equals 530. Okay, what will be the second step is to getting other dimensions of the footing, which is the area of the footing itself. Okay, calculating the footing area or B capital and D capital. For calculating the footing area, we have to use the load at serviceability limit state because the allowable soil pressure is at service limit state. So here we have to use it as serviceability limit state also. So the load in this case will not be the ultimate load, it will be only the service load. So we have to calculate the total service load. We call it NS instead of N ultimate, N service. Okay, so the N service equals what? Equals dead load times 1 plus live load times 1. Here the load factor will be always 1, not 1.4, 1.6 as in the case of the ultimate. But here the N service, we add dead load plus live load plus the weight of the footing itself, because the self weight of the footing will be applied to the soil and it will increase the stress on the soil. So we have to consider the W of the footing or the weight of the footing. Okay, so let's apply this. So the NS equals dead load plus live load plus weight of the footing equals what? Equals the volume of the footing times the density of the concrete. Volume of the footing equals the area of the footing times the H. Okay, and gamma C here refers to the density of the concrete. So let's put the values here. The dead load in this example was 1000, live load was 350, and here H of the footing was zero point 0.6, because here we are going to use it as in meters to get the load in kilonewton. So 0.6, gamma of the concrete assumed as 24 kilonewton per meter cube. Area of the footing is unknown. This is the unknown that we need to find. So the total service load equals, multiply this, it will be 1,350 dead load plus live load, plus here 0.6 times 24, it will be 14.4 times the A. And the A here is the area of the footing, which is the missing information that we need to find. Okay, once we know now the total service load, okay, it has a constant value here and something multiplied by the area of the footing, then we will say soil bearing pressure at service load shouldn't exceed 200 kilonewton per meter square, and any stress here or pressure equals the load divided by area. Okay, so the allowable pressure 200 equals N service divided by the area of the footing. What is in the service? We will substitute in the service by this term here, which is 1,350 plus 14.48. So let's do that. So 2,000 or 200 here, 200 equals 1,350 plus 14.4A. This is the N service divided by A. So you will have here two A's here. You rearrange this equation and you will be able to find the A. The A, or the area of the footing, equals 1,350 divided by 200 minus 14.4. So if you want to find always the area of the footing equals the service load, dead load plus live load, divided by the allowable bearing pressure minus this term here, which is the thickness of the footing times the density of the concrete. Okay, so it will be 1,350 divided by 200 minus 14.4. It gives us an area of 7.27 meter square. So this is the minimum area of the footing that if you use, you will be sure that the pressure under the soil will not exceed 200. It will be exactly 200. So this is the required area. We have to use a provided area greater than this value, or at least equal to that value. Okay, what will be the area? This area of the footing, we can use a square footing, we can use a rectangular footing based on the column. If we have a square column, we are going to use a square footing. So we can get directly the square root of this value. So to get the square root, it will give you 2.6 something. So in this case, we use 2.7 meter times 2.7. So D capital equals B capital equals 2.7. And the provided area is 7.29 meter square, which is slightly greater than this value. Okay. How we got this 2.7 again? You got the square root of this value, so it will give you 2.69. Okay, we round it to 2.7, or we can do it 2.75. It's okay. Always be in the conservative side, like to be in the safe side and to have some factor of safety. So the second step here, we calculated the area of the footing. The provided area is 7.29, and the dimension of the footing is a square footing of 2.7 meter for each side. Step 1 and step 2, we got the dimensions H, D, small, and the area of the footing B and D. So now we are ready to continue for our design. The third step, we have to get the earth pressure at the ultimate limit state, because for the design of reinforcement, checking shear, all of these are at the ultimate limit state. So we need again to get the stress under the footing or the soil pressure at the ultimate limit state, not at the surface limit state. So to do that, we have to get the N ultimate. We already did that on the first step. So the N ultimate was 1,960 kilonewton. Okay, to get the earth pressure, any pressure here at the ultimate equals the load at the ultimate divided by the actual area of the footing or the provided area of the footing, which is 7.29. So this is in kilonewton, and this also in meter square. So it will be kilonewton divided by meter square. So the earth pressure is 268.9 kilonewton per meter square. Okay, so we can draw it now. This is our footing. The footing is 2.7 meter times 2.7 meter, and the H is 600. The D is 530. and the soil pressure at the ultimate limit state equals 268.9 kilonewton per meter square. These dimensions here, this is the width of the column, and this dimensions here, we can get it from, it equals the 2.7 here, the total width, minus 0.4, all divided by 2, it will give us 1.15. So if you say 2.7 minus 0.4, it will give you this distance and this distance, divided by 2, so you can get only from one side. So how to design now? We need first to design for reinforcement in both directions, and then we check for shear. We have direct shear and we have punching shear. So for the reinforcement, as you know, the critical section for calculating the reinforcement and for maximum bending moment, it will be at the face of the column. So we have to get the moment at the face of the column here. To do that, we have this soil pressure. So M here equal this soil pressure times this hatched area. It will give us a concentrated load here times the lever R. We explain this in video number 1 if you want to go and check video number 1 or the first video about footing. So the moment equal P, this is kilonewton per meter square, multiplied by this area. So meter square will go with meter square, so it will be only kilonewton as a concentrated load here at the middle, multiplied by this distance here, which is the L over 2 of this is L. So it will give us the bending moment here, the maximum bending moment, like as a cantilever. So it will be 268.9, this is P, times B capital times L, which is this one times L, where this is the L here. So it will be 2.7 times 1.15. Once you calculated this value, it will be easier for you. So you calculate and put it on the drawing. You will not make any mistake. So 2.7 times 1.15. Okay, now we have a load multiplied by half of this distance, L over 2, which is 1.15 divided by 2. Okay, you get the multiplication of this. So we have the moment here is 480 kilonewton meter. Okay, this moment about this line here at the face of the column. So we can use this moment to get all the reinforcement in the horizontal direction here. Okay, so let's get the reinforcement. The reinforcement we'll use now the British standard equations, or if you are using any other code, you can also use its equations. So K equals M over FCU BD square. M is 480. Don't forget to multiply by 10 to power 6 because we need it now in Newton millimeter. Divided FCU is 35. B here is the width of the footing, which is 2.7 meter, and now we put it 2,700 millimeter. D square, D is the depth of the footing, it's 530, and again, don't forget the square here. So all of this will give us a small value here, 0.018. It is less than 0.156, so it means we don't need compression steel. Okay, usually in footing, you will not need a compression steel, and this number will be very safe. Okay, so it is less than 0.156. We don't need compression steel. Okay, continue on that. Calculate the Z over D. Z over D equals 0.979 greater than 0.95. So according to the code, this value cannot exceed 0.95. So we'll take the Z here equals 0.95 times D equals 0.95 times 530. So it will give us a lever arm Z of 503.5. Okay. For Z over D here, if you don't know this value, equals 0.5 plus the square root of 0.25 minus K divided by 0.9. So the only thing here in this equation here is the K that you calculated in step number 1, K divided by 0.9. Okay, we found that the Z here equals 0.95D. This is the maximum value, so it gives us this value. Now we can get the reinforcement, AS, area steel required, equals M over 0.95 FP yield times Z. Substitute with the values of M, FP yield, and Z. So we can get the required area of the steel reinforcement in the horizontal direction or X direction equals 2,182 millimeter square. So we can now choose a diameter and we can get the number of bars. So we choose diameter 20 millimeter and we got 8 bars, T20. T here, it means we are using high yield steel or FP yield 460 megapascal. We can calculate also the spacing approximately. okay, just to check we will not exceed the maximum allowable spacing. And based on that, we can calculate AS provided. AS provided, you can see here, it should be greater than or at least equal to AS required. We prefer to have it greater than the AS required to just to be in the safe side. So AS provided is greater than AS required, and we choose 80-20. What is the minimum diameter that we can use for the footing? If you remember, for the columns, we use 12 millimeter as a minimum diameter for columns. Also, we can use 12 millimeter as a minimum diameter for footing. However, it is better to use even greater diameter or greater size than 12, but 12 is okay. Now, we designed for the reinforcement in the X direction, and because this footing is exactly square footing and the column also is a square, so this reinforcement, which is 80-20, will be provided in the horizontal and in the vertical direction, in both directions. You don't need to redesign for the vertical dimension or vertical direction because it is a square footing. Once you calculated one side, the other side will be exactly the same. So check for minimum reinforcement and spacing. The minimum reinforcing according to the BS code is 0.13% BH. So 0.13 divided by 100 times the B times H of the footing. So 0.13 times 2,700 times the H here, which is 600, not D, divided by 100. Okay, so all of this will give us, this is the minimum required area. We can see that the minimum area here is less than the AS provided, so it means we are satisfying the minimum reinforcement area required by the code. Also, we can check about the spacing. The spacing here is about 330 something, less than the maximum allowable spacing by the code, which is 750 millimeters. So it means it's okay. So it is easy to check about the minimum reinforcement and the spacing. It is very important to check about the minimum reinforcement here, okay, because you can see the reinforcement, even the minimum reinforcement is a big value. So just to check this one to be sure that you are satisfying this condition required by the code. Now we finish checking, calculating the reinforcement in both direction. We check the minimum reinforcement and the spacing. So now the coming step, it will be about checking shear. Checking shear is very important in footing because the load is big load coming from the column, and we can have a shear failure. So it is not similar to the slabs. If you will go back to my videos about slabs, you'll find that always when we go and check the shear is very safe, very safe. Okay, so sometimes you will not do check for shear, but in the footing, it is very important to check for the direct shear or one-way shear, and also check for the punching shear because it could be the collapse. It can result in a collapse of the footing if you didn't check the shear. So to check the shear, we have two shear checks. The first one, check shear at a distance D from face of the column. Here is the column. You will go at a distance D from the face of the column. So this distance will be D, will be 0.453, 530. And we have to check to get the shear force here. To get the shear force here equals the stress, ultimate stress on the soil multiplied by this hatched area. So it will be 268.9 times B times L, where the L is this distance here. So we can calculate this L. This L in this problem equals 2.7 minus 0.4, all divided by 2, again minus 0.53, it will give you this distance here, which is 0.62. So the V capital equals 268.9 times 2.7 times 0.62. So it will be 450 kilonewton. Okay. This one is the shear force that we need to use to get the shear stress. So this is the shear force is 450 kilonewton. To get the shear stress equals the shear force divided by the shear area. So it will be divided by this width here times D. Okay, this width times D. This will be the shear failure plan. So it will be 450. Don't forget again to multiply by 10 to power 3 to make it as Newton, and divided by the shear area here, B times D, put it in millimeter. So you will have the shear as Newton per millimeter square. This is a famous mistake that many students and engineers are doing and getting like unsafe shear, because you sometimes forget to use here millimeter. You put it as meter, okay, and you put this without 10 to power 3. So if you divided 450 divided by 2.7 times 0.53, you will have a very big value here, and you will think that the shear is unsafe, but this is only because you did a mistake. So everything here should be in Newton and millimeter. So the load multiplied by 10 to power 3 to make it Newton, and the dimensions here in millimeters. So the result here will be Newton millimeter square, Newton per millimeter square. So now we need to check for shear. This is the shear stress. We have to get the VC, or the shear carried by the concrete. According to the BS code, we have to calculate 100 AS over BD. So 100 times area steel in the or area of tension steel divided by B times D, which is 2,700 times 530. So it equals this value. This shouldn't exceed 3. Then we have 400 over D. It is less than 1. So according to the code, is saying we can take this as 1. Then substitute this value into the VC equation, which is 0.79 times the first term here, 100 AS over BD to power 1 over 3 times 400 over D to power also 1 over 3, but should be less. This value here should be greater than 1. So we used it as 1, and multiply by FCU divided by 25 to power 1 over 3. All of this divided by 1.25. Okay, I didn't go in details through this equation, but you can see it in the videos about designing of slabs, one-way slabs and two-way slabs, and also you can see it when we design for shear in the beams. Okay, so the shear carried by the concrete equals 0.396 Newton per millimeter square. We can see that the shear stress is less than the VC. So the shear stress due to shear loads here or forces here is less than the shear stress carried by the concrete. So in this case, we can say that the direct shear is okay and it is safe. What will be the coming step? Again, it is very important step to check the punching shear at a distance 1 over D from the face of the column. According to the BS code, this will be the critical section for the punching shear at a distance 1.5 D from the face of the column from all sides. Here, because this is a square column, so this distance will be 1.5 D and 1.5 D from all sides, and you have here also a square area here. Okay, so the critical perimeter for shear, which is this perimeter, this distance here, equals column perimeter plus 8 times 1.5 D. How this coming? Because it equals this distance plus this one. Okay, these corners here, 3D plus another 3D, another 3D, another 3D. Okay, so 8 times 1.5 D. You have 1.5 D here, 8 times 1, 2, 3, 4, 5, 6, and 7, 8. Okay, plus the column perimeter, which is this one, and this one here, and this one here, and this one here. Okay, so you can do it as you want. You can calculate the distance here, 0.4 plus 1.5 D plus 1.5 D. So you have this dimension, multiply by 4, you can get the perimeter. This is one method, okay? Or you can use this equation here, which is the column perimeter plus 8 times 1.5 D, okay? So getting this distance here, it will be 7,960 millimeter. You get it in millimeter, okay? Then we have to get the area that within this perimeter here. We can say area punching here, or AP. This is will be what? Will be this distance times this distance, because it is a square now. So equals horizontal times vertical. Even if you have, this is a rectangular area, if you have a rectangular column, so it will be this dimension times that dimensions here. So it will be 0.4 plus 3D, 1.5 here plus 1.5. And because this is a square area, so it will be 3D plus 0.4 square. 3D plus 0.4 square. If you have a rectangular column here, so it will be 3D plus 0.4 plus 3D plus whatever the other dimension of the column. So this one multiplied by this distance here. So it will give you an area in meter square, 3.96 in meter square. Okay, so from here we can now calculate the punching load. How much it will be the punching shear force. V punching equals the stress under the footing
multiplied by this hatched area. This hatched area equals what? Equals the total area of the footing, 2.7 square, minus AP, which we calculated here. So it will be the stress under the soil multiplied by total area of the footing minus AP. So we will substitute this by 7.29. AB we just calculated 3.96, and it will give us 895 kilonewton. Again, this area here, put it as meter square to have this as kilonewton, because the area here also is in meter square. Okay. So once we calculated this shear force or punching shear force, we need now to get the punching shear stress. Okay, a stress equals a force divided by area. So the punching shear stress equals V small equals V punching divided by the punching shear area here. So it will be the area at this perimeter. You can see here how it will be this area here that will have the plan of punching. It will be through the depth of the footing at this perimeter. So to get this, the area that the punching will go through, so it will be the depth of the footing, okay, this depth here, times this perimeter, okay. So it will be U, the perimeter that we calculated, millimeter, times D, which is 530 millimeter. And again, now this is in millimeter because now we need to get a stress, so it will be Newton per millimeter square. So this dimension and this dimension in millimeters, and the load here, it was in kilonewton multiplied by 10 to the power 3. So we got the punching shear stress is 0.212 Newton per millimeter square. Again, we can see that the punching shear stress here is less than the VCs that we calculated in the previous check when we checked for one-way shear. So this one is less than the VC. It means the punching shear is okay. So by doing that, you finished the design. You designed for reinforcement. We checked for direct shear. We checked for punching shear. All of them are safe. So now we can make our drawing. The drawing is always will be a plan of the footing showing the reinforcement in both directions and dimension of the footing, as you can see here, and an elevation of the footing showing also the reinforcement in the horizontal direction or perpendicular direction. In this case, you can see that we have the same reinforcement in both directions because this is a square footing. It is 8T20 and 8T20. We put the dimensions here. In the elevation also, we put the depth of the footing, the total H of the footing, 0.6 meter. And here we use the blinding concrete 50 millimeter, and this also the reinforcement in both directions. Also here you can add the reinforcement of the column, indication of the reinforcement of the column. You don't need to write anything here because we are concentrating mainly on the footing for now. Okay, just as a final note here, according to the code, the distance from the face of the column here, which is the maximum critical section for bending moment, to the end of the bar, it should exceed the development length. Okay, so it should be greater than 40 times the bar diameter, and 40 times the bar diameter equals 40 times 20 because the bar diameter is 20, so it is 800 millimeter. When we check this distance here, it was 1.15 meter, so it is greater than the 800. So it means we don't need to make a hook here or to make another hook on the other side because this distance is greater than 40 times bar diameter. So this is you don't need a hook, and this will be your reinforcement. This is the end of the presentation. In the coming one, we will go through a footing with under eccentric loading. Thank you for watching. Please don't forget to like, subscribe, and share the video to share the knowledge. Thank you, and see you in a coming video. Goodbye.